I had a question earlier from the homework, pretty good question. Any questions from homework stuff? What's happening next class? What's happening Wednesday? Quiz, yes. Okay. What's the quiz on? 1, 2, and 3, 1. TCAS. Okay. Was anyone not here last time? We worked on this last time, if I remember correctly. Yeah. Yeah? Okay. You can at least have a copy of this. Were there any, for anybody who was here last time, were there any lingering questions on this? I'm pretty sure. Let's do this real quick. Let's kind of quickly go over this. So this first, now real quick. My number one is not everybody's number one. Yes, do you guys remember that? This was the problem where I had to go to groups, so I put this problem in various places on this, so I would stagger when I was running to different groups. Do that for yourself when you become a teacher. So these were using the base 4 pieces. The idea with this was, if I have 3, and I add 2, if I move that over, it becomes a long and a unit. So this would be, what was this answer?
11.
Yes, 11 base 4. So 1, 1 base 4. 1, 4, and 1, 1 makes 5, which is 3 plus 2. KCAS. You with me? So I'm not going to go through the rest, but unless you want me to. This one, where did you have to be careful? Because you didn't have to be careful. 0 and 0, 0 plus 1, 0 plus 2, 0 plus 3. The zeros you don't have to be careful at all. Whoop-de-doo, whoop-de-doo. The ones you have to be careful in one spot, yes? 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5. Okay, what do you put down here?
10.
Good. Because now you've reached the base. In base 10, how do we write 10? 1, 0. In base 7, how do you write 7? 1, 0. Yes? I like it. And the great thing is, what would this be? Yeah, because now I can count on by 1 as they go across. Yes? So the nice thing is, I think I looked at all the groups and pretty much everybody had the 10 in the right place. This is what your students are going to feel like, and I keep saying this, when they're doing base 10 addition. It's going to be just as new to them as this was to you. So they're going to need some help to figure out when the next digit rolls over. It's like a speedometer. And of course, little people aren't going to know what the hell a speedometer is, so it's a bad analogy for them, but you guys know, so I can tell you. Now real quick, oh geez. I didn't get around to everybody about this, I don't think. But if I just fill us in, this is going to be so exciting. Everybody just stay in your seats. Oh, Jeff, good job. 5, 6, 10, 11, 12. 6, 10, 11, 12, 13. 10, 11, 12, 13. And then what goes here? 14, because 4 is allowed in base 7. So some people had some trouble with 14. I don't blame you. Where's the next place we would have issues? Yeah, what's the base? So you can't have 17, correct? So if I try to do, if I'm about to get this, what should it be? Let's do this directly, because I had a question like this on the quiz. If I think I'm supposed to get this, what should it be? 20. Same way if a kid said 28, 29, 2010. No, 30. Every time you hit the base, the next place increases by 1. That's exactly how base 10 works. You just don't think of it that way unless I put you in a different base, and then you have to really be careful about it. Okay, I like it. How do we answer this question now? Say again? Yeah, you can't just do 12 minus 4, right? But you look and you say, okay, where did I get? Here's some 12s, yes, there's some 12s. But which one came from a 4? Well, let's see, this one came from a 4, yes? So what method am I using if I'm doing this? I find a 12. It came from a 4 plus. So what method am I using to do the subtraction? What method am I doing for this? I found the 12, and I see that 12 came from 4 plus 5. So what method is that? If I want to do 12 minus 7, and instead I do 12 equals 4 plus what method is that? Do it again. No, I see what you mean. So not a strategy. I agree with you. That is an easier way because it's built on addition. And when students are learning subtraction, you want to try to connect it to addition because they kind of are more comfortable in addition. Yes. The way I've written it, isn't it a problem where something is missing? So what is it called, this method? What's missing? So one method for subtraction is called missing addend. Yes? You with me? So the things involved in the addition problem are called addends. So if I rewrite subtraction as the total equals part plus something, that's missing addend. What is missing to make that complete? So of course here we got 5. So what would you do here? What would you have to do first? Yes. So 11, and I want to see where it came from a 5. So here it came from a 5. So again, I'm going to do missing addend, 5 plus. So what do I put here? Here's 11, and it came from 5 plus 3. And then I do the same thing. Find 10, and I want to see where it came from a 3. So what's 10 minus 3? 4. Now real quick. Does anybody appreciate that? The thing I just said would make no sense outside of this room right now. 10 minus 3, of course, is 4. We all know that. And real quick, why does that make sense? Because what is this really? What is this in our base? 10 base 7 is actually the number what? 7. And 7 minus 3, sure enough, is 4, yes? Okay. By the way, whoever were the robots, I'm on your team for the moment. This one, was it missing addend or take away? Now, technically you could argue one, but there's one that just immediately is the right answer. Eva has 3 Oreos. You can pretend to be Eva. You're sitting down, you have 3 Oreos. You feel pretty good. You got freaking Oreos. Hopefully some milk, right? You look over, there's Jim sitting next to you. He's got freaking 5 Oreos. Yeah, you with me? You're not all that great with numbers yet, but you know that's not fair. So what method would the subtraction represent here? What would she be most curious about? I mean, she's curious how many more he's got, but what do you guys think? Would it be missing addend or take away? Missing addend. She's like, how many more would I need to have the same? I'm like, give me some more. How many? Then you got to figure out how 2 would give us the same. Yes? Okay. Maybe. So when I ask a question like that, you could argue take away would work. When she looks over, she sees 5, she takes away 3, so she's what she would do. But it's most immediately missing addend. Now, if I want to use the set method, I got my Eva with 3 Oreos, and I got my Jim with 5 Oreos. And what I think one group did was they had a little area and they said, all right, so now if I put 2, they're the same. So then 5 minus 3 must be the 2 that she needs to make them the same. So that's missing added. How many cookies would you have to add to make them the same? Okay. And I think I at first I should have put comparison on there because it's actually more like a comparison problem. What do you have to be careful about on number 4? It's actually related to what you have to be careful about here. When you make a base 6 number line, same problem, right? What do you have to be careful about? So then if you do 2 base 6 plus 5, 1, 2, 3, 4, 5. Okay. It's going to be as weird as that is to you. It's going to be that weird to the little dude. It's going to be even weirder because they're generally less comfortable numbers in general. Right? Okay, maybe. Okay. So, what we're getting into today is multiplication and division. We're getting into section 3.2. We're not, so several things that don't exist for us in this class at this moment. Negative numbers don't exist for us. That's an idea that they bring in later. Fractions don't exist yet, which I feel like a lot of you guys might be very happy about. I don't know. Is that pretty cool with fractions? Pretty cool with fractions? Some of you guys are like, screw frac, okay. Shoot, you gotta really mean it. Come on, you go. Yes. Can somebody tell me, like, what's the first kind of problem that you could run into multiplication for? What's the like a base level problem you could run into that requires multiplication? Like a basic example that you could give a student that would require multiplication to answer. But where did it come from? A physical situation. Physical situation that would require multiplication. So really what I'm asking is what the hell does multiplication mean? Yeah.
Sets of adding. So Bill has 3 apples. Timmy gives him another 3, and then John gives him another 3.
Okay. Yeah. Okay. Because all right. So that would be 3 plus 3 plus 3, which of course we could write more condensed as 3 times 3.
So, whatever the second number is, that's how many times you're adding the first number.
Oh,
so
okay.
7 times 3, that means
Other way around.
7.
Other way around, which yeah, becomes a big issue. All right. At the most basic, multiplication is repeated addition. Let me just do a point. Repeated addition. So for example, if I wanted to do 3 plus 3 plus 3, I can write that as 3 times 3. Or let me do it, sorry. It's really weird to teach this class because you use the x for times until you get to algebra, right? And it's so ingrained in me to not use the x for times. I'm like, oh yeah, that's right, I have to. Okay. Do you guys remember real quick where they stole that symbol from multiplication? We brought this up before. No, I like that though. It is a Roman numeral, but no. It was kind of a weird thing where we made points out of pieces from different sets. It's okay, it's a weird name. Cartesian product. Oh crap, did everyone. So very quickly, if my set A had A and B in it, and my set B had C, D, E in it, A cross B would be all the sets you can make, all the points you could make using parts of each. yes? So how many total points would you end up with? 2 times 3, 6. And the Cartesian product uses that notation. Okay. So, if I want to do this visually, like with a set method, I want to do 3 times 2. I would do like, all right, so real quick, you brought up a really good point. This would be 3 groups of 2. So now I'm thinking about, I can't remember which way you said it. Now, obviously, we are well aware that 3 times 2 is the same thing as 2 times 3. But can you guys, very quickly, underneath 3 times 2 on your notes, can you write 2 times 3 and try to represent that visually? So what's going to be different? The answer is going to be the same. We know that because we know commutative property. Little people are not going to know commutative property. They're going to be connecting everything they're learning to physical things they can touch. Yes? So 3 groups of 2 things. Great. That means 3 times 2. What's 2 times 3 mean?
2 groups of 3.
2 groups of 3 things. That is physically very different, right? If I have 3 groups of 2 people, I can envision 3 groups of 2 people. 2 groups of 3 people, very different physical situation. Different social situation, different in all these kind of ways. Mathematically, they both end up with 6 people, right? This is going to be another situation where parents are not going to understand what you're doing with their kids because you have to connect to the kids' physical interpretation of things. And then later you show, oh yeah, commutative property tells us these mathematically come out to be the same thing. So this would be 2 groups of 3. Both are 6, right? Okay. How would I do this? How do you think I would do 3 times 2, coming back to 3 times 2 with the measurement model? What was the measurement model again? Yes. Number line, yes.
Yeah.
Yes. I like it. I appreciate that. All right. Real quick. Do you guys know, do you guys have anybody in your life who recently had a baby or something? Anybody? Yes? Do you guys know, I remember when my friend had her first kid, this is a long time ago, but she taught them sign language. So she learned sign language while she was pregnant, and then when her baby was born, she taught them sign language. Yes? Why do you think that's important for a little person?
Because babies can't talk.
Babies can't talk, but they can move their hands. Yes? Also, very often they might be kind of shy or whatever. Maybe they don't want to talk a lot, but they could do something really quick with their hands, and that is less out there. You guys know with me? So I don't know, real quick, I just like that some of you guys were in the air doing something. That's fun. I just want some kind of a feedback. That'd be great. Measurement model is a number line. So how do you think I would do 3 times 2 on a number line? What are you going to have? How many of what? 3 times 2 is how many of what? 3 times 2 is how many ones? 3 times 2 is it 2 3s or 3 2s? 3 2s, right? If you forgot, you can look right there. 3 2s, yes. So how do you think you would show that on a number line? All right. So the important part there is set this up, and then you want to go in 1 2, right? You want to go in 3 packets of 2 steps. Do another two-step. Is that like a country line dance? And then two steps, right? Is that okay? So again, that is a number line representation of three groups of two. So you're not gonna believe what 2 times 3 looks like. What's 2 times 3 gonna look like? Pretend like my scale is good. I'm gonna do 2 times 3.
Just jump to 3.
Yeah, just do 1, 2, 3, and then another 1, 2, 3. And both times, of course, they get 6. It's crazy. Okay. Very different physical situations. I can't stress this enough. All this math stuff is something we humans invented on top of all the other stuff. We learn how to walk. So we learn steps naturally. We know what steps are. We have to connect that to the idea of math. Yes? So this is why we do 3 times 2 differently from 2 times 3, because they are physically different. They are both 6, and everybody knows it's freaking 6. And parents are going to be like, just tell them it's 6. And you're like, I got to connect it to the physical reality they experience. Maybe. Commutativity is another thing on top of that they learn later. So very quickly, main things about multiplication. These are called factors. So if I have A times B, these are factors. The result, does anyone know what the result is called? Product. That's crazy sauce. Okay. So that's repeated addition method. That's the repeated addition method for multiplication. Set method and, set model and measurement model. This is just kind of the definitions of the parts of it. The second way to look at it, besides repeated addition, is called the rectangular array. This one I call the ice cube tray, because what's the most basic geometrical idea that uses multiplication? It's kind of a wide open question, I know, I'm sorry. Like, if I want to figure out the area of the floor in here, what 2 things would I have to measure? Yeah, how long that wall is, how long that wall is, and then I would multiply, yes. So literally, if I wanted the square footage, I would know how many feet that is, how many feet that is, and when I multiply them, I actually see how many little squares that are a foot by a foot would actually fit on the floor. That's square footage. It's actually little foot squares. So rectangular array method, 2 times 3 in a rectangular array method would be this. So this is 2, and this is 3. Do you see that 2 groups of 3 idea still? Yeah? And this is there's just nothing but places where parents are not going to understand. What would 3 times 2 look like? Yeah, it would just be 3 by 2. And one way to kind of show students visually that these are the same is one of those pictures just as the other one. How do you get one of those pictures from the other one? You just take that picture and you, how would I make one of the pictures look like the other one? Just rotate it, right? So physically, those 2 represent the same object. So then it makes more sense. Oh, commutative, 2 times 3 is 3 times 2 because the object they both describe is the same, just rotated. All right, I really want you guys with me. I don't know if any of you guys ever realized that's how you can explain commutativity. And I keep saying commutativity. Is everybody cool with the commutative property? Where you can just switch things? That is the first physical level of how to explain commutativity. 2 times 3 and 3 times 2 both reference the same exact ice cube tray, just rotated. So now a student can start to grasp, oh, it doesn't matter what order, the number comes out the same. Although physically they are different things. If I put a thing in my backyard, a garden, this way versus garden that way, that is very physically different. You with me? You go in my backyard, if it's this way versus that way, that's going to look very different. Yes, that's a physical difference, but one is just rotated. So a big part of later mathematics, not like really late, is to have a student start to tear apart the math from the physical situation. 2 times 3 is 3 times 2 is 6. But the physical situation is different. Okay, I'll stop. I'm sorry. Come back. Right there. Bye-bye. Oh, real quick. By the way, these are both measurement model. They're both related to a number line. It's basically the idea of the XY plane. Real quick. Number line is like the x-axis. You put another number line going up, that's the y-axis, yes? And if I actually made a grid, then it would be exactly that, yes? And I can make a grid going up 3 over 2, yes? Is everybody with me? That's why the rectangular array, the ice cube tray, is officially called the measurement model. If you want to see the set model, this is kind of silly, but it is what it is. If I want to do 2 times 3 rectangular array set model, it would look like this. You can do it, Jeff. Yes. There. Do you guys see how it's basically the same thing? But the funny thing is, I call those are the ice cubes, and the measurement model is the actual ice cube tray. Yes? Those are like the Oreos. Yes. Coming out of my tray of Oreos. Okay. Oh, we have talked about this, right? Yeah, we talked about Cartesian product before, did we? Or was today the first day you heard me say that phrase? Today was the first day? All right. Neat. Sorry. I've taught this class so many times, I'm like, oh yeah, I forgot I even talked about it. So real quick, I'm sorry, we'll come back to this. Cartesian product. I thought for sure it was back in chapter 2. So just to give you a different example. So the Cartesian product, yeah, I know we've talked about that before. It was in chapter 2, yes, when we did sets. Okay, I'm not going completely insane. For the slightest moment I thought, well, there it is, Jeff. Can't remember shit. Time to pack it up. All the Cartesian product is make every pair you can using one element from the first set, comma, oh shit, nobody told me that, 7 just said. One element from the first set, comma, one element from the second set. Right? So, I mean, if I do A cross B, the first element's going to be from here, the second element's going to be from there. So I can just keep going, and if I do this very systematically, I can just exhaust the squares, then exhaust the triangles. You guys see what I mean when I say exhaust? Like, yes, we live it every day, you exhaust those triangles. No. Use up all the options for each. And then, of course, you get how many? How many points? 6. So, again, like I said earlier, we stole that for times, because the number of things in this is 6, which is the number of things in here times the number of things in here. Okay, so the idea of Cartesian product existed before we formalized the notation for multiplication. So it's more of a review. Then we have, so that was the third way, sorry. So we have repeated addition, we have rectangular array, we have Cartesian product, and now we have tree diagram. Anybody ever heard of a tree diagram?
Yes.
Where have you guys done tree diagrams before, if you've done them before? Does anyone think they've done them before, tree diagram? Do you remember where you did them?
Maybe probability.
Yes, totally. Probability is the most common place to see these numbers. What's probability based on? Sure, chance. And what increases the chances of something happening? You get more of them. So probability is completely based on the counts of how many things. Yes? A tree diagram. So, when I constructed these, how many options did I have for the first spot? How many options did I have for the first spot? What could go in the first spot? What could go there? What shapes? A square? Triangle? Circle? You guys with me? So I had 3 options, yes? So I could pick a square, I could pick a triangle, I could pick a circle. After I picked any of those, what could I then pick from B, from set B? What could I pick from set B?
4.
4 or B. So if I picked a square, I could then pick 4 or B. If I pick a triangle, 4 or B. A circle, 4 or B. So does that jive with what you remember with? And of course, you can keep going if you want to, what are we going to do? Okay. Then you have to turn your paper that way so you can actually grow this thing. Okay. And if I look at the ends, I end up getting these back. So if I go down this path, what do I collect? If I go down this path up here, I pick up a square and a 4, yeah? So, I could just recreate all of these, just in a more visually structured way. So that's a tree diagram. Another place, if I want to do probability, has anybody, I don't know, ever bought a car, used car, whatever, new car? Has anyone ever dreamt about buying a car? Okay. What decisions go into buying a car? Well, what kind of car you want? So if let's say you're focused on you want this, you want a Subaru Outback. So then what could you decide? What's the most visually obvious things you could decide about your car? Yeah, the outside color and the inside color, yes? So you could make a tree diagram if you had a certain car from a certain place, and let's say the interior you could do white or beige, and the exterior you could do green. I got to pick things that are going to work here. Green or yellow or purple. That's horrific. Goryork. Werb and Goryork. Okay. Then I can make a tree diagram. White. What did I say? I can make beige. And then green, yellow, purple. Green, yellow, purple. You guys kind of with me? You can see how many total options there are. Has anybody ever heard of how many pizzas can you make if you have like a choice of 15 toppings and it's in the millions? Have you guys ever heard that before? If you want to choose a pizza and there's like 15 toppings you could choose from, the number of pizzas you can make is in the millions because of all the different combinations. And you can imagine that if I kind of build a tree, well, I could pick pepperoni, mushroom, blah, 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 blah. And then once I pick one of those, I can pick any of the other ones. And once I pick any of those, I can pick any of the other ones. And once I pick those, I can pick any. Can you imagine how many branches there would be? Do you see how big this gets very quickly? Okay, I'll stop. Okay. By the way, today's going to be a bunch of me talking, so just get used to it. Here we go. This is the way it happens. So some properties. Whole number multiplication. We have our favorite closure. Those are my favorites. I love closure. Anybody remember what the hell closure was?
Which means the product is a whole number.
Exactly. Whatever set I start with, the results better still be in that set. So I like the idea of closed. It's closed under multiplication as long as you can stay in the same room. So if this is the room with whole numbers, when I multiply two whole numbers, my answer is going to be in the room. It's in the room with us. You guys kind of with me? Okay. I don't know. I always love that. But it's not the psychological closure, right? It's the mathematical closure. Multiplication is very much closed over whole numbers, because if I take a whole number times a whole number, the answer will be a whole. You can't help but do that. Whole. Somebody remind me what whole numbers are again? Where do they start? What number looks like a whole? That's where they start. 0, 1, 2, 3. So they're counting numbers plus 0. Commutative. We already talked about commutative. And that's when we did, 3 times 2 is 2 times 3, and you can show that visually very easily. Okay. And then associative is really cool. I'm not going to try to draw this. Here, there's a neat picture. Did I tell myself where it was? I did. Jeff, you're amazing. So let's look at a picture that a computer made instead of a picture I might try and make. All right, so real quick. Shoot. That's 3 times 4 down there, yes? That right there. Jeff, do this. There you go. Okay. Okay. That's 3 times 4, yes? 3 times 4, yes? And if I want to do 2 times 3 times 4, I would just do 2 of those. Is everybody with me? If you put those together and then tear them apart this way, now you have 4 2 times 3s, yes? So this is 2 3 times 4s, and this is 4 2 times 3s. Is that cool? I always appreciate when somebody just humor him. He'll keep going if you just, yes, that's amazing. But visually, this is really satisfying, I think. And it'd be cool if there was something I could actually, like Legos would be good for this, right? Okay. Thank you for humoring me. I appreciate that. So, let's see. What is the multiplicative? Let me just put this down here, just in case you want to look at it later. Let me also unfreeze this. Right. Page 112. What is the multiplicative identity? What does identity mean? What was the additive identity? What was the additive identity? What was the number you add that doesn't change the identity of the number? 0. So if you apply the same logic to this, what number do I multiply by that does not change the identity of that number that I'm multiplying? 1. 1 times 7, it's still 7. It doesn't change its identity. 2 times 7, now it's a whole different number. What the hell? So identities are just the things you operate with that maintain the original number. That's why the additive and multiplicative are different, because the operations are different. So this one, a times 1 equals 1 times a equals a. Oh, Jeff, what are you doing to yourself? Okay. Blah, blah, blah. Oh, and then we have distributive. This one I might be able to handle drawing. Let's see. 2 times 3 plus 2. do you think I would draw this? Should I try to draw it, or should I just show you? I'm always iffy with my drawing. Here. Oh, this is different. So what do you guys think I could do here to do this? So like, how do I do 3 plus 2? So let me see. If I do 3, 1, Jeff, you can do it. If I do 3, yes, 1, 2, 3, plus 2. Okay, I'm doing this weirdly, but you'll see why. Is that cool? So this is 3 plus 2. Is that cool? Now the reason I did it like this is because now I want 2 times that, so I want to double this, yes? Pretend like I drew that to scale. So do you all agree with me that this is 2 times 3 plus 2, because I have 3 plus 2 twice. Is that cool? Now, how does distribution work algebraically? How would this be rewritten? Distribute for me, what would you do? Don't give me the answers, tell me what the work would be. 2 times 3? 2 times 2? Plus, yes. And you can see, if I just take this guy, isn't this 2 times 3? And then I put this next to him. That is 2 times 2. And that's the same object. Yes, I just broke it in parts. So you can imagine, again, Legos, not a bad option. Of course, if you use Legos for very young kids, choking hazard, you gotta be careful. Also, they'll probably create whatever, and they won't do what you want them to. We'll see. That's why I highly suggest, and I'm gonna do this with certain manipulatives, when I give you stuff, I give you like 5 minutes, and I kind of pretend like I'm busy. Just see who remembers this. And then I walk around and see if anybody's making something out of this stuff. So, we'll see. So let your students do whatever the hell they want to, not like choking hazard business, yes, make sure it's safe. Just to get used to manipulating whatever the shit is, and then you come in with, okay, good, all right, let's use it this way, and then you show them how to use it the other way. Then they're more comfortable with what they're doing. When I teach 126, for example, how often do you guys use compass? Do you guys know what a compass is? Well, it's got that really pointy end, and it's got the pencil, and then you can put it somewhere, you can open it up to a different radius, and you can make a circle, yes? So what I did last semester when I taught 126, I gave the compasses out, compi. I gave many of those out, and then I just said, go ahead and create something. Go ahead and create something. So, you guys kind of with me. How long had it been since the people in that class had used a compass? Maybe some of them had never used a compass. This is very possible, yes? I didn't show them how to use the damn thing. None of that. I just pointed it out, be really careful, it's really sharp. And then I had people come up and show their work. It was really cool. So people made cool shit. But what they were doing while they were doing that, I didn't show them how to use it. They were learning themselves how to use it. And they were making all this nifty stuff, and they were realizing how the hell all the parts of it work. You guys with me? And I didn't have to like guide them, I just let them play. Then they're more comfortable with it. They came up with it themselves, how to use the damn thing. And then we did some specific constructions of things, yeah. Okay, so you want to do something similar when you have manipulatives in your classroom. Let them just do whatever they want to safely before you impose certain things you want to do with them. I gave away the game, but we'll see who remembers that later. So that's distribution. By the way, real quick, just to go a little beyond what we just talked about. If I had this, you would distribute, correct? Because why do you have to distribute? If I just to push this beyond where we really are. This is stuff you guys have seen before. What does order operations say I must do first? What's the very first thing in the good old order operations? Please excuse my dumbass son. Parentheses. Now, what's wrong with this problem in that respect? What the hell is x plus 5? Yeah? You're like, x plus 5 is purple. Why not? No, I don't know what this shit x plus 5 is. So, real quick. Remind me what multiplication is. Fundamentally, what was the first way we defined it? The most fundamental interpretation of multiplication is repeated addition. So what does 2 times anything mean? You have how many things doing what? I have 2 of these adding. So how can I rewrite this then? And then I can use associativity and commutativity and all that kind of business, yes? So then I'll end up with how many x's? 2 of them, Jeff, and how many 5s? 2 of them, that makes 10. And then we're like, screw that shit, just bring the 2 through. So distributive property is a shortcut. You guys see that? Because if I have 70 times x plus 5, I don't want to write x plus 5 70 times. Screw that. I'm just going to know what would happen and go there. Yes? You guys kind of, has anybody ever seen that? So me, if I was a student and I was taught the distributive property, I'm like, wait a minute. You could just go against what order operation says. You've been drilling that in our heads this whole semester, dude, math boy. But then you say, no. You're reconfiguring the problem. If I write it like this, then I could use associativity and commutativity. All right, okay. Shimo. Oh, okay, so watch this. How could I use distributivity to help me figure out this problem? I want you to do this by hand. By the way, I'm sorry. I have to force myself to use x for multiplication. So that says 32 times 57 plus 68 times 57. Do you all agree that would suck to do it by hand just directly the way it's written? 32 times 57, 4, carry the weight, right? You guys agree with me? But do you guys see something nice about this problem? What's common? So what we're going to do is we're going to do distributivity in reverse. What did somebody distribute? I'm thinking backwards. What number was given to 2 other numbers that we're adding? So I can write this as 57 times what? 32 plus 68. And what's 32 plus 68? What's 2 plus 68? 2 plus 68. 70 plus the other 30? 100. Those are compatible numbers, yes. 3 and 6 is 9, 2 and 8 is 10. That forces it over to 100. And what's 57 times 100? 5,700. You just put 2 zeros on, right? Maybe. So I don't know if you've ever been shown, this is what like the mental calculators do. You ever seen these people that can do all these calculations in their head? I know you think well, I don't know if you've seen me do enough stuff. I got one skill I like to show off. I do this kind of thing in my head to make things easier, right? So you need, chapter 4 is going to be mental mathematics. And we'll be doing stuff like this and some other tricks. Okay. So what about this? What if I had, you could do it, Jeff. Yeah, except one little thing. Like, this would be 40 times 8 plus 60 times 8 plus an extra 1 times 8, right? For example, you guys with me? This is 40, 60, and then the extra 1. Then here, this would be 8 times 40 plus 60 plus 8. You guys kind of with me? 41 times 8 is 40 times 8 plus 1 times 8. Is that okay? What does 41 times 8 mean? 41 eighths. What is 41 eighths? 40 eighths and 1 eighth. It's 41 eighths. Yes? Now, real quick. All right, some of you guys screwing your face up because you're like, I wouldn't have done it that way. I don't know. Do you guys see what I did? Do you guys see what I did? 41 and 60 suck. I would rather have 40 and 60. So you can push the extra 8 on the side. Maybe. Okay. Then you get, trying to get us to a point, I want to show you some, we can watch little people doing their work. Yeah, let's do this real quick. We have a very similar thing to what we talked about before. And this is what people are more used to, multiplication tables, right? So if I have, I don't want to do all of them, dear God. Yeah, that's plenty, okay. I'm doing times. Obviously the 0 row and 0 column kick at, they're the real MVP. And of course the 1 row and the 1 column kicks ass. And of course I've got the same idea. I have commutativity, so I don't even have to worry about the stuff like over here. Because once I know 2 times 1, I then know 1 times 2. Does that make sense? We did the same thing with the addition table. 2 is similar to when I added two numbers, a number to itself. 2 is just doubling things. So normally students pretty much get the idea of doubling things. So this will be 4, 6, 8, 10, blah, blah, blah. And same thing here, this will be 2, 4, 6, 8, blah, blah, blah. But then again, we got commutativity to cover those. Okay. Another one that's really good, what do you think the easiest chance? Let me give you an example. 3, 6, 9, 12, 15, 18. What's the easiest example of that for a student?
It's not that. Can we go back to the last one?
Let's do the what now?
The last one where it was like 42 times 8.
Oh yeah, sure.
I'm really trying to understand, like, okay, so you got the 40 times 8, and you have plus 60 times 8. And then you got another 8.
Well, how many 8s do I have here?
1.
How many 8s do I have right here? 41 8s, yes?
Mm-hmm.
So I put 40 of them right there, and the extra one of them right there. That's all I did. What does 41 times 8 mean? That means 8 added to itself 41 times. So I put 40 of them there, and that means I had one extra one to do. So if I have, so 5 times 8, for example, is 8 plus 8 plus 8 plus 8 plus 8, right? So if I had 5 times 8 plus 6 times 8, I can make this 5 times 8 plus 5 times 8 plus 1 times 8, because this is 6 8s, yes?
Yeah.
Okay, that's all I did. So if I have 41 8s total, I could put 40 of them right there, and the other one of them right there. There's 60 right there. Now the 40 and 60 make 100.
Okay.
48s and 68s is 108s. Yeah, you're good. I don't want to go too fast past this stuff. Because we're past the point where we even try to do this in our heads almost ever, yes? Now, obviously, I say we, I'm doing all this stuff in my head a lot. And that's why I can do it so well. But this is the kind of stuff that you could be doing to really quickly do something in your head. You don't have a calculator with you. Well, now it's really funny because the meme is the old-time math teacher would say, what if you're somewhere and you don't have a calculator? And we're like, we have a calculator with me all the damn time now, math teacher. Nah. But you should know how to use numbers. We're humans. We made them up. We should know how to use them. Okay. So, real quick. Do you think that 3, 6, 9, 12 is a really easy chance for students to kind of pick up and understand how to keep going? Can they memorize that all the way up to like 100 or something? No. So even you, if you had to do it, in fact, I say every third one, and people make mistakes when they pick their numbers. So 3, 6, 9, 12, 15, 18. It's really easy. You got to slow down at some point, make sure you're going by 3, correct? What is the easiest number to chant by? What do you guys think? 5. 5, 10, 15, 20, 25. Because it keeps repeating. 0, 5, 0, 5, right? That's easy as shit. So therefore, multiplying by 5 is easy as shit. If I go 0, 5, 10, 15, 20, this is 0, 1, 2, 3, 4, right? 5 times 1, 5 times 2, 5 times 3, 5 times 4. So 5, 10, 15, 20, 25, forever, yes? Maybe. Screw you, Jeff. If doubling is cool, then 4 times something is just doubling twice, yes? So this would be double 10, which is 20. So then you can use that to fill in the 4s, row and column. Are you guys at all with me? What I'm trying to show you is when you're first teaching a student how to even begin constructing a multiplication table, you can kind of go by these rules. Doubling. 0 and 1, easy as shit, yes? Doubling. The 5 chant. 4 is doubling twice. That's just a really good thing to kind of like realize as a human. Oh, 4 multiplied by 4 is just doubling twice. You guys with me? So multiply by 4 times 27. You double it twice. That makes it much easier to do in your head. Okay. And I can't stress this enough. I really hope this isn't true. You don't have to absolutely love math, but you need to realize everything you say about it is going to seep into their heads. So my biggest concern, and I had teachers like this, and thankfully I don't think I was too young, but I had them when I was older, that it was really apparent that the teacher didn't like math himself. You with me? How well do you think students are going to understand math after that class? Not well. Because when I'm looking at this, I have taken classes where it's really obvious the teacher didn't give a shit about the thing they're teaching. I'm talking like history or something, right? And that's not my wheelhouse. I like history, but it's not like my thing. You with me? So I'm in the history class, and I'm thinking, this guy doesn't even like this shit. Why would I like this shit? What the hell? Have you had math teachers that seemed like they didn't even like what they were telling you? You kind of with me? So imagine if you are doing that, potentially, to a little person. That is going to fundamentally, you're setting the foundation. The younger the student you're teaching, you're setting their foundation for how to look at math. I need you to really understand this. I want anybody who's taking this class that gets to become a teacher, I want you to be fully aware of this. I don't want it to pressure you, but you have to be very careful. I think you guys know what I'm coming from. So when you're showing students really basic stuff, you have to find ways to invest yourself in it. Yes? Now, the great thing is the students are going to eat this up. The younger the student is, the more they just want to take in everything. So it makes it a little bit easier for you to kind of like work with them. Okay. Okay. So a couple things real quick. How would I do this? 5 times 37 times 2. This is kind of silly, but how would I do that? How would I do it in a way that makes it easier? Because what do I have to do the parentheses first in this case? What's the only operation in the whole thing? Multiplication. And multiplication is commutative. And it's associative. So, I mean, which two numbers are compatible? Which two numbers want to go together? 5 and 2, 10. So I would do 5 times 2, and then multiply by 37. Would I get the same answer if I doubled this first? Hell yeah. Would it be a lot easier to do 5 times 2 first? Hell yeah, because if I do 5 times 2, I get 10, and then that's 3, 7. Chaboom. Whoops. This is a really little thing, and I'm pretty sure at least some of us do that when we have to do this in our everyday lives. What was the other one? Oh, yeah. Let me see. what do you think you could do to make this better? There's two kind of ways that come to my mind. But if you had to do that by hand, and you haven't even been shown how to carry, you with me? So yeah, you can put 25, put a 9 underneath it, but you haven't been shown how to carry it. How could you rewrite that to make it easier?
25 times 4.
Yeah, okay. Why is 25 times 4 nice? Because it's freaking 100. And students normally get that. They normally understand quarters and dollars. Yes. Because if they got enough of those, it was 7-11, get some twizzlers and whatever. Yes. So I got, one way to say this is I've got 9 25s. Well, what's 9 25s? It's 4 25s and, sure, but what's 5 25s? 4 25s and, 1 25. I'm not used to writing extra times. So that's 100, 100, 25. So that's 2, right? 25. So if you want to see what I really did, isn't 9 4 plus 4 plus 1? Yes? And then I could distribute 25 to each piece. You guys see that? You guys see that? You guys know you could do that any damn time you want to. Does anyone see a different way to do using subtraction? I used addition, yes?
25 times 10.
Yeah! 9 25s is 10 25s, take away 1 25, right? So if I take 9 times 25 and I write that as 10 minus 1 times 25, distribute, that's 10 times 25 minus 1 times 25. That 10 times 25 is 250. 1 times 25 is 25. That's crazy. 250 minus 25? 225, same answer, of course. No, where did it go? There it is. Okay. Same answer, 2 different ways. Okay, I like it. I like it. I like it a lot. So, I mean, I do not know how much you guys have ever done stuff like we're doing right now. Obviously, you did it way back in the day, but I don't know if you've done it more recently. People kind of remember distributive property, commutative property, associative property. You remember the names at least. Sometimes you're like, I don't know, remember what's what. These are examples of how those properties are useful. Instead of just being, you got parentheses. No, they're actually useful for doing things in our head. Okay. What time we got? Oh boy. Sorry, I just got a lot to get through. What do you guys, alright. You're not going to believe what we're about to do. Alright, so let's just finish out the 4 main operations. Remind me what multiplication was most fundamentally? Multiplication is repeated addition. What do you think division should be then? Repeated subtraction. So let me just start right there. This is something I know none of you remember doing unless when he has a job at a school and you see his kids doing this. So for example, if I wanted to do 48 divided by 17. Now real quick, is that going to have a remainder? Can you tell very quickly if it's going to have a remainder? Hell yeah. Now here's how repeated subtraction works. This is so cool. And there's no reason we would do this now, because don't we have long division? Do you all understand that long division is freaky as shit to someone who has never seen it before? There's a lot that goes into it. So this is another place a parent's going to be like, why don't you just put the 17 and the 48 and do it the normal? You know, because there's a lot of shit that goes into that. That's not an automatic thing. So you begin with what it really is. So this is kind of cool. This is kind of nifty. Start with 48. Start subtracting 17 until you can't anymore, meaning the next one will make it negative. If I subtract 117, how much do I have? 31. If I subtract another 17, how much do I have? Can I subtract another 17? No. So how many 17s did it take? 2, and what's the remainder? That's the answer. 2 remainder 14. Yes? Now I'm real quick. I'm not going to point out who it was. The rest of the day, I'm going to live on the facial expression I just saw on somebody's face. Because I know I'm a geek. I know I'm a geek. That is kind of cool. How many of you guys remember ever seeing division done like that? Some of you guys? Yes? Most of you guys, probably not. Yes? Isn't that cool? At this point, when you start division, you all agree division is one of the harder operations. Everybody just loves long division. But a little person is going to understand subtraction by the time you start teaching them division, correct? So again, do you notice every time we talk about a new topic, the very first thing I do is I tie it to a topic we had talked about before. And again, that's called scaffolding. So you want to kind of get a student really, really comfortable with subtraction, and then when you get to division, you're like, guess what? You could look at division like subtraction. Now, then you get to a problem like 5,847 divided by 21. You're like, then you say to them, do you want to subtract 21 from that forever? And they're like, no. Because that would take a long time. Yeah. So let's make this quicker. Let's figure out how to make it quicker. You guys kind of with me? And then you start to work on division by itself. How do I make it quicker from there? But this is a beautiful place to start. They know subtraction. They can live with subtraction. And then the leftover is exactly that. It's just whatever's left at the end. Now, can somebody tell me what this actually means when I say 2 remainder 14? There's a way to rewrite 48 buried in there. What's the 2 mean again? 217. So 48 is 2 times 17. But that's not true until you put plus 14. You guys see that? That is literally what that means. 17 would have went in evenly if it was 14 less. If I had had 48 minus 14, if it was 34, 17 would have went in evenly. There was just 14 extra things. Or if it was 3 more, then it would have been 3 17s, right? It would have been 2 plus another one. I don't know if you guys are with me. Okay. There's a lot of cool shit with division. There's actually, it's okay, Jeff. Okay, we'll get there. Yeah, we'll get there. Okay. I wanted to start with this because it's such a cool thing to do right off the bat. This is repeated subtraction. I'll formalize this here in a minute. All right, Jeff, you can't spell and you can't write. That's fantastic. Okay. At least you can still talk. That's what. Okay. More fundamentally than this, though. More fundamentally than this. There are physical situations that result in division. And of course, just like there were physical situations that result in multiplication that were different, but they might come out to the same number mathematically, right? 2 times 3 and 3 times 2. With division, you have these 2 main ways of looking at it. One is a sharing idea, and the other one is called a measurement, which we've seen before, which is fantastic when we use words over and over and over again. Let me remind myself what this book calls it. Oh, it's just okay. Sharing division and measurement division. Sharing is exactly what you would think. What situation would you physically want to share that would result in division? Yes. So you have like 12 cupcakes and 4 people. Yes? So sharing is exactly what it sounds like. Sharing kicks ass. 12 cupcakes and 4 people. How many cupcakes does each get? Right? That would result in the math required being 12 divided by 4. You guys with me? Measurement the kind of physical situation that would result in 12 divided by 4 would be this. Measurement is different. So measurement says, okay, what if I have 12 cupcakes? And we put them 4 boxes. Wait, let me make sure. Oh, that's right. I gave it away. Damn it. Yeah. Put into, how do I want to say this? Because I had a different example. Sure. Okay, there we go. Put into boxes of 4 cupcakes each. There we go, Jeff. So I have 12 cupcakes, and I put them into boxes of 4 cupcakes each. How many kids can get a box of cupcakes? Do you see the physical difference? Maybe. 12 cupcakes. The first one was 12 cupcakes. I have 4 people here, including me. We each get 3. The other one is I split 12 cupcakes into boxes of 4 cupcakes. How many kids can get a box then? They're both 12 divided by 4. You with me? Physically, the first one is 4 kids, and the second one is 3 kids. Yes? The first one, they each get 3 cupcakes, and the second one, they each get 4 cupcakes. So the math was 12 divided by 4. The physical situation for both is different. Do you guys see the difference between sharing and measurement? Maybe. It's kind of like you have Kool-Aid, and you want to measure it out in like cups. You with me? So you're like, that's the measurement division. Sharing is exactly what you think. I want to share with the people around me. Okay. All right, I like it. Now I'm kind of like elsewhere there. Now, real quick. So you have repeated subtraction is the most fundamental way to look at division, which makes sense because division is the opposite of multiplication. Multiplying is repeated addition. Division is repeated subtraction. Subtraction had missing addend. Division has missing factor. So for example, if I want to do 12 divided by 4, I can say that equals something. So 12 is 4 times what? And why does missing factor make sense? It's pretty cool, by the way, that the x up there is times, just not like the variable x. Because I'm looking at it and I'm thinking, you guys got it with me? So that's just like missing addend, same idea. And why does this make sense from a scaffolding perspective? Because they will come into division having worked with multiplication. So if you can make it related to that, they can connect to it better. Okay. Blah, blah, blah. Oh, real quickly. Let me put it up here. So that's missing factor approach. So then this would equal 3. That's amazing. Here are the words for describing a division problem. And these are kind of weird. Do you guys know what the result is called of a division problem? Yeah, so with addition it's the sum, with subtraction it's the difference, with multiplication it's the product, with division it's the quotient. And here we get really quite freakadelic here. This is the dividend, and this is the divisor. Now, I'm not overly concerned with these words, except for quotient. That's a big one, right? Dividend, divisor. Divisor kind of makes sense. It's what you're dividing by, so divisor makes sense as a word. Dividend, that sounds more like a stock thing, but we'll be all right. Now, real quick. What would the physical situation be behind this? if I was thinking of a sharing, I got 5 people, right? I got 4 other people and me, and we made $0 today. So then how much does each person get? 0. So there's a physical interpretation behind 0 divided by 5. So the result is a nice number. It's a real valid number. You guys might know where I'm going with this. Why is 0 divided by 5 equals 0, by the way? Because, real quick, I don't think, have I written this yet? Like, real quick, what's 20 divided by 5? Because 20 is 5 times 4. So it's just rewriting it like a missing factor approach, right? So why is 0 divided by 5 0? Because 0 equals 5 times 0. Keep doing that. So, of course, where am I going with this? What is 5 divided by 0? It would have to be the number so that 5 equals 0 times that number. Is there a number that does that? Like here, isn't 4 the number defined in such a way that when you multiply by 5, you get 20? Do you agree with me? Let me say that again. I said that in a strange way. But do you agree that 4 is a number defined in such a way that when you multiply by 5, you get 20? You would need a number that's defined in such a way that when you multiply by 0, you get 5. Do we have any number defined that way? So this is undefined. You guys know that word, yes? When you try to divide by 0, it's undefined. Did any of you guys call it something different? 5 divided by 0, did you call it something different, like infinite? No? Or did most of you guys call it undefined? Or are you like, I don't know, man. Okay. But if you ever did call it undefined and you had no idea why, that's literally why. There's no number defined that when I multiply by 0, I get 5. Oh yeah, so here's something kind of neat. What about this one? Okay, you ready for this? So what's 0 divided by anything? Almost anything. 0. What's anything, almost anything divided by 0? Undefined. So what is 0 divided by 0? Alright, can you write it like this? Like this. It would have to be 0 would have to equal 0 times something. When is that not true? Is that only true for a certain number? Is 0 equal to 0 times just 7? Is that the only number that would work? I need you guys with me. 0 equals 0 times what? What could you put here and that would be true?
0.
You could put 0.
Anything?
Huh? Anything, yes? 7 times 0 is 0. 8 times 0 is 0. Square root of 11 times 0 is 0. Negative 14 over 93 is times 0 is 0, yes? Okay. So this one is trippy. It's not undefined because everything works. But then can you tell me what the answer is? No. So this one, to be honest, I forget what does the book even call it something? No. It just points out this is weird. I'll tell you the actual word for it. Indeterminate. It's kind of worse than undefined in a way. It means I cannot determine what the answer is. Why not? Because anything works. It's like being a detective. And I'm like, okay, I got to whittle down my people that it could have been that killed this guy. What do we know about the person that killed this guy? They were human. Thank you so much. Thank you. Great. Great job. Commendable. You're going to get a promotion. So it could still be anything. You with me? 0 is 0 times the thing. It's just like saying, oh, the guy was human. All right, you've done the same thing. It could still be anybody. It could still be anything. Okay, maybe. Oh my God, you guys doing all right? Shit. Sorry, today was just going to be a lot. I'm sorry. We're a little. I want to make sure we don't get too far behind, so I just got to throw a lot at you. Yeah, okay, beautiful. I got one. Oh, here we go. Okay, coming back to the thing we did earlier. If A and B are whole numbers with b not equal to 0. Sorry, a and b are whole numbers. Any whole numbers, doesn't matter. But b can't be 0. Then there are numbers we call q and r, so that a equals bq plus r. I think something else that they didn't put in here is a has to be greater than or equal to b, and r has to be between 0 and b. So this is exactly what we did earlier when we did this guy here. Do you see how a equals bq plus r? 48 equals 2 times 17 plus 14. 14 is the remainder. 2 was the quotient. That was the main answer. That's what the q means. So this is all this is saying is if I have like 16, well, that's equal to 2 times 7, this is a bad example. 16 is equal to 3 times 5 plus 1. There we go. So if I'm dividing 5 into 16, I get 3 remainder 1. So the theorem says if I have two numbers a and q where a is bigger, a and b where a is bigger than b, I can always find a way to write it like this. That's a very complicated way of saying when you divide stuff, you can get a remainder. Yeah.
Could you go up for 1 second, please?
1 second. Sorry. I'm an asshole. All right, let's see. Yeah, good. All right. Very happy for you because I'm about to shut up. I'm going to show you some little people working with this stuff. Let me stop recording so I don't get a copyright strike.